Welcome to today's paper reading. Today's paper is titled, Learning to Compress Prompts with GIST Tokens. This paper was published in the 37th Conference on Neural Information Processing Systems, NeurIPS 2023, by Jesse Mu, Xiang Lisa Li, and Noah Goodman from Stanford University. The abstract highlights the challenges associated with prompting in language models, which include occupying valuable input space and being computationally inefficient due to repeated encoding. To address these issues, the authors introduced gisting, a method that compresses prompts into smaller sets of GIST tokens that can be cached and reused, thereby improving compute efficiency without additional training costs. This approach results in significant performance gains, including up to 26x compression of prompts, a 40% reduction in flops, a 4.2% speedup in wall time, and storage savings, all while maintaining minimal loss in output quality. Gisting is a method proposed to compress arbitrary prompts into a smaller set of transformer activations using virtual GIST tokens. This approach adopts a meta-learning strategy, allowing the model to predict GIST prefixes without additional training, thereby generalizing to new instructions. Gisting achieves significant efficiency gains, with up to 26 times prompt compression, 40% reduction in flops, and 4.2% faster latency during inference. The implementation involves instruction tuning with GIST tokens and a modified attention mask, ensuring no extra training cost while maintaining output quality. Figure 1 illustrates the efficiency trade-offs in utilizing language models, LMs, for multitask capabilities. Prompting, while retaining the multitask abilities of LMs, is inefficient due to the repeated encoding of prompts. Fine-tuning or distillation methods are more efficient but require retraining for each task. Gisting, as shown in the top right of the figure, compresses arbitrary prompts into smaller sets of GIST tokens, which can be cached and reused, thereby saving compute resources and generalizing to novel tasks at test time. Each vertical rectangle in the figure represents a stack of transformer activations, highlighting the process of prompt compression and reuse. In the context of instruction fine-tuning, we have a dataset D consisting of task prompts T, optional inputs X, and desired outputs Y. The goal is to train a language model, LM, to predict Y given T and X. However, concatenating T and X has limitations due to the LM's context window constraints and the computational inefficiency of long prompts. Gisting offers an alternative approach by learning a compressed version of T, denoted as G, T, which allows for faster inference without the need for additional training. Figure 2 illustrates the modifications made to the attention masks in transformer language models, LMs, to facilitate prompt compression into GIST tokens. For decoder-only LMs, such as GPT-3 and Llama, the causal attention mask is adjusted by masking out the lower left corner of the triangle, ensuring that tokens cannot attend to preceding tokens. In encoder-decoder LMs like T5, two changes are implemented, preventing the input from attending to the prompt in the encoder, and preventing the prompt and GIST tokens from attending to the input. This setup encourages the model to compress prompt information into the GIST tokens, enhancing computational efficiency and generalization capabilities. The approach to learning gisting involves using the language model, LM, itself as the GIST predictor. This method leverages the existing knowledge within the LM and allows for the learning of gisting through standard instruction fine-tuning, with modifications to the transformer attention masks to enforce prompt compression. This means that gisting does not incur any additional training costs beyond standard instruction fine-tuning. Specifically, a single GIST token G is added to the model's vocabulary and embedding matrix. Given a task and input pair, T, X, T and X are concatenated with K copies of G in between. The model is then restricted such that input tokens after the GIST tokens cannot attend to any of the prompt tokens before the GIST tokens, but they can attend to the GIST tokens. This forces the model to compress the prompt information into the GIST prefix. The required changes are illustrated in Figure 2 and involve simple masking changes that can be implemented in roughly 10 lines of code. The experiments begin with the creation of the Alpaca Plus dataset, which includes 130,321 examples and 104,664 unique tasks. This dataset is designed to be diverse and challenging, crucial for training models that can generalize across various tasks. The models selected for these experiments are Llama 7B and Flan T5XXL, both of which are trained with varying numbers of GIS tokens to explore different levels of prompt compression. The evaluation methods employed include RuGel for lexical overlap, ChatGPT for semantic comparison, and human evaluation to validate the model's performance and the reliability of automated evaluations. The GIS token models demonstrated near-identical RuGel and ChatGPT performance on scene instructions, achieving 48.6% and 50.8% win rates for Llama 7B and Flan T5XXL, respectively. When it comes to generalization to unseen tasks, the models maintained competitive performance with 49.7% and 46.2% win rates for Llama 7B and Flan T5XXL. However, on the most challenging out-of-distribution human split, there was a slight drop in win rates to 45.8% for Llama 7B and 42.5% for Flan T5XXL, though these numbers remain competitive with the positive control. Figure 3 presents the impact of varying the number of GIS tokens on the performance of two models, Llama 7B and Flan T5XXL. The graph displays RuGel and ChatGPT scores for different numbers of GIS tokens, with dashed lines indicating the performance of positive and negative control models. Error bars represent 95% exact binomial confidence intervals, which split ties equally between models and favor the positive control in case of an odd number of ties. The compression factors are calculated by dividing the average token length of the validation split by the number of GIS tokens. This analysis helps in understanding how prompt compression affects model performance and generalization capabilities. Table 1 presents the results for models using single GIS tokens, comparing RuGel and ChatGPT scores among GIS, TF-IDF, and positive/negative control models. The scores in parentheses are normalized between the positive and negative controls. Key findings include the GIS model's competitive RuGel scores, particularly in the unseen and human splits, and their high ChatGPT scores relative to the controls. Notably, the GIS models achieve near-identical performance to the positive controls in terms of win rates, demonstrating their effectiveness in handling unseen tasks and out-of-distribution data. Table 2 presents the human evaluation results for single-token GIS models, comparing their performance against a positive control. The data includes win rates and inter-annotator agreement metrics for two models, Llama 7B and Flan T5XXL, as evaluated by three human annotators, H1, H3, their average, and ChatGPT. The win rates show that Llama 7B achieved a 52.3% win rate over the positive control, while Flan T5XXL achieved a 40.6% win rate. The inter-annotator agreement, measured by Cohen's kappa, was 0.24 for Llama 7B and 0.33 for Flan T5XXL. Notably, ChatGPT exhibited similar levels of agreement with the human annotators, with an average kappa of 0.29 for both models. These results suggest that using ChatGPT for evaluation is comparable to adding an additional human annotator, reinforcing the findings from Figure 3. Table 3 presents the efficiency improvements achieved through GIS caching strategies. The table records CUDA wall time and flops for different caching strategies, none, instruction, and GIST. It highlights the absolute and relative improvements of GIST caching over the alternative strategies, with 95% confidence intervals. Notably, GIST caching demonstrates a 40% reduction in flops and a 4 to 7% improvement in CUDA wall time. Additionally, it enables the caching of up to 26 times more prompts compared to full instruction caching, using the same amount of storage. The efficiency gains of GISTing in compute, memory, and storage are significant. In terms of compute efficiency, GISTing provides a 40% reduction in flops and a 4 to 7% decrease in wall time for the models tested. For Llama 7B, there is a modest 1% speedup in wall time despite a negligible decrease in flops. Memory efficiency is improved by the ability to compress 26 tokens into one, freeing up space in the input context window and allowing for more prompts to be cached. Each token in the KV cache requires 1.05 megabytes of storage, but gisting allows for caching up to 26 times more prompts using the same amount of storage. This is particularly beneficial in scenarios where many prompts are cached across a large number of users, leading to significant cost savings over time. Table 3 presents the efficiency improvements achieved through gist caching strategies. The table records CUDA wall time and flops for different caching strategies: none, instruction, and gist. It highlights the absolute and relative improvements of gist caching over the alternative strategies, with 95% confidence intervals. Notably, gist caching demonstrates a 40% reduction in flops and a 4 to 7% improvement in CUDA wall time. Additionally, it enables the caching of up to 26 times more prompts compared to full instruction caching, using the same amount of storage. Gisting offers a novel approach to adapting language models without the need for gradient descent, by predicting the prefix of the adapted model. This method can be compared to hypertuning, which also predicts model prefixes but requires input-output pairs. Gisting, however, operates in a zero-shot manner, predicting the prefix solely from language instructions. This approach is not only more efficient but also conceptually simpler, as it leverages the language model itself as the hypernetwork, requiring only minor adjustments to attention masks for prompt compression. Additionally, the concept of compressing prompts in gisting is related to efforts in improving memory and long-range sequence modeling in transformers. Unlike the compressive transformer, which uses a learned convolutional operator, gisting employs the model's self-attention mechanism for compression, jointly learned with instruction fine-tuning. Finally, gisting's restriction of attention masks draws from efficient sparse attention methods in transformers, offering an input-dependent sparse attention mechanism tailored for improving the efficiency of prompting workflows in language models. The gisting framework achieves significant prompt compression, up to 26 times, while maintaining output quality. This results in a 40% reduction in flops and a 4.2% speedup in wall clock time. However, this method has limitations. It may lose some nuance of the original instructions, and its performance on edge cases is not well understood. Practitioners should carefully evaluate the compute/accuracy trade-off before deployment. Future work could explore retrofitting existing frozen language models, focusing on compressing very long prompts, and improving compression performance through gist pre-training. The authors acknowledge the Stanford Alpaca team, particularly Xiang Li, for their assistance with alpaca data and fine-tuning processes. They also thank Gabriel Poja for providing the codebase used to collect human evaluations. Additional gratitude goes to Xiang Li for helping with debugging and ensuring the reproducibility of the open-source codebase. Financial support for this research is provided by the Open Philanthropy AI Fellowship, which supports JM, and the Stanford Graduate Fellowship, which supports XLL. Thank you for watching.